Okay, in this next video for Math 1560 Calculus 1 at U of L for fall 2017, we're going to look at the method of substitution for indefinite integrals. Now for indefinite integrals, meaning simply antiderivatives, substitution is nothing more than the reverse of the chain rule. So remember how the chain rule goes. If you have a composition of functions, so if I have a function h, which is written as the composition of two other functions, f and g, and I want to calculate the derivative of h, remember the chain rule says you first take the derivative of the outside function, you evaluate the inside function, and then you multiply by the derivative of the inside. Okay. In terms of the Leibniz notation, remember we can introduce this intermediate variable u, right? Sometimes we were already doing this substitution for derivatives, and so if you think about that u substitution that we did in the derivative context, it's exactly what we're going to do in the integration context, right? So instead of so y here, right? Y is h of x, right? And so we can think of that as f of u, where u is equal to g of x. And so what we can do is say, well, what's dy dx? Well, in the Leibniz notation, it's the product dy du times du dx, and so we, again, we can use the chain rule like that. You could also think of this in terms of differentials, right? If we kind of drop the dx's here, then what we have in terms of differentials is that dy is f prime of u times du. What is du? Du is g prime of x times dx, right? And so if we substitute this in, then what we have is that dy is f prime at g of x times g prime of x times dx, right? So there's your chain rule. But what we're going to do is we're going to split this off, right? We're going to split off this part and then recognize that, well, this is basically our u here, right? And so reversing things, if somebody gave us this integral, if they said, okay, I want you to integrate f prime of g of x, g prime of x times dx, right? And okay, maybe they, you're not given this f. Maybe it's just f, right? But we know that there's an antiderivative for this little f. Okay, so we know an antiderivative for little f. So we have a big F prime. So what we can do is we can say, okay, let's let u equal to g prime of x times, let u equal g of x. So du is g prime of x times dx. Well, then our integral f of g of x, g prime of x times dx is going to be, well, it's going to be simply, so g of x is u, g prime of x times dx, well, that's du, so it's just f of u times du. But we found this antiderivative, right? So this is big F prime, and so now we can say, oh, but that's big F, right, plus a constant. But if we started with something in terms of x, we shouldn't leave our answer in terms of u, so then we substitute back in. What was u? U was g of x, so we get f of g of x plus c. Okay, so that's the general procedure. We'll see how this looks in a few examples. But the main thing that you have to kind of keep in mind when you're running into this, when you want to do this substitution method, well, what are you looking for? You're looking for composition, right? Remember that chain rule comes along whenever you're dealing with function composition, and if we're trying to reverse the chain rule here, well, then the way we know that we need to reverse the chain rule is we see function composition in our integral. So when we see this f composed with g, that's our clue that maybe there's a substitution we have to do. The other thing that you hope you see once you identify that composition is that the derivative of whatever is inside that function is sitting somewhere else in your integral so that you can make the substitution. Okay, oops. So here, just summing things up, what we just worked through. If somebody gives you an integral where you recognize that the integrand is essentially just the derivative of something obtained using the chain rule, then your u, this new variable that you introduce, is whatever the inside function is. You recognize the composition. You look for what's the one function that you see plugged into another function. That's your u, right? Then you take the differential of u, so du is g prime of x times dx, and you plug everything in. Now, a couple of things to keep in mind. One is, if you see this right away, you don't have to go through all the steps. You can if you want to be sure, but if somebody handed you something like, say, e to the x squared times 2x times dx, and you said, oh, e to the x squared times 2x, I know what that is. That's just the derivative of e to the x squared, right? Well, there's nothing wrong with just jumping straight to that answer if you see it. If you don't see it, then what you do is you say, okay, I have this x squared being plugged in to the exponential function, so that tells me that I should let u equal to x squared, and that means that du is 2x times dx, and then this becomes the integral of e to the u times du, and then we say, oh, but e to the u is its own antiderivative, so e to the u plus c, so it's e to the x squared plus c, substituting back in that u is equal to x squared. Okay, so if you see it right away, jump straight to the answer. One of the things that might happen is you might not have that 2 there. You might not be so lucky to have the 2. So if that 2 is missing, right, then, well, you still make the same substitution, right, because you kind of have no choice. You still have to make that same substitution because you still have to get rid of what's on the inside function that's being composed with the outside function. You've got to deal with that inside function. But what you can do is you can say, all right, I need to let u equal x squared because I see that the x squared is trapped inside the exponential function. I only have an x sitting out here, but that's okay. If du is 2 times x, or 2 times x times dx, I can just multiply both sides of this equation by 1/2. 1/2 du equals x times dx. And then I can say, okay, so this becomes e to the u times 1/2 du, right, because x dx is 1/2 du, and then you can always pull the constant out, so you can write that as 1/2 e to the u du, and so this is 1/2 e to the u plus c, and then we put back in that x squared, right? So if you're off by a constant, you can always make adjustments like this to make sure that you get the right thing. Okay, here's a couple more examples. For the first one, it's kind of similar to what we just did. The inside function here is the 5x, right? We know how to integrate cos x. We don't quite know how to integrate 5x, so what we can do is we can say, okay, u should be 5x. That means that du should be 5 times dx. So we can divide both sides of this equation by 5 like we just did on the previous slide. The other thing you could do if you want, here's a trick that you could do. You could say, well, that's 1/5 of the integral of 5 cos 5x times dx, right? And then you've got that 5 dx sitting inside, and we know that we didn't change anything because constants can move inside and out of the integral, so this is the same as what we started with. Okay, and then even from here you might recognize that 5 cos 5x is in fact the derivative of sine 5x, and jump straight to the answer. And if you didn't notice that, then of course you could do the intermediate step where you say, okay, this is 1/5 times the integral of cos u times du, and then say, okay, that's 1/5 sine of u plus c, and then put back in your u equal to 5x to get to the answer. Alright, next one, similar story. The way we know we have to do substitution is we look at the integral and we see that we have composition, right? This polynomial function, the x cubed plus 1, is being plugged into the exponential function. That tells me that I'd better take u to be x cubed plus 1, right? I substitute the entire inside. So x cubed plus 1 du is going to be 3x squared times dx. And again, I could divide both sides by 3, so 1/3 du is x squared dx. And I say, okay, x squared dx, I have that sitting right there. Okay, so this is my u, so that's e to the u. The x squared dx is 1/3 du. So I put everything in, and what I've got is the integral of e to the u times 1/3 times du. And so that gives me 1/3 e to the u plus c. So 1/3 e to the x cubed plus 1 plus c. Alright, let's try a couple more. The third one, it's not so obvious what your substitution should be. Right? There is no composition. Is there a composition? Well, okay, there sort of is, but it's not jumping out at us. So the other thing that we might look for is, do we see one function whose derivative is sitting elsewhere? Well, the kind of more complicated of the two functions here is the log function. So then we say, well, let's just see what happens, right? If all else fails, choose part of your integral and substitute it and see what you get. Well, if u is equal to the natural log of x, that means that du is 1 over x times dx. And then I say, do I have a 1 over x times dx sitting there? I do. Here is my 1 over x times dx. Okay, so let me slide this over. We'll just do a really long equal sign. There we go. By the way, actually, that's how equal signs were written once upon a time. Equal signs used to be much longer. The equal sign was meant to represent parallel lines, because what could be more equal than the slopes of two parallel lines? That's where that notation came from, in case you were wondering. So the 1 over x times dx, that's our du. That leaves me with log x in the denominator. So 1 over log x becomes 1 over u, and then all that's left is du. Okay, so what is the antiderivative for 1 over u? It's the natural log of u. So this becomes the natural log of, and remember, put absolute values in just to be safe. So the natural log, absolute value u. So it's log x, right? Because u was the natural log of x, plus c, and you're done. Okay. We'll end with one more. This one is actually kind of tricky, and I'm going to give you the setup, and then I'm going to leave it for you to finish off. If you try to just substitute this one, you're going to find that it's kind of tricky. There's no obvious substitution to do right off the bat. And so now again you start looking and you say, okay, there's this x to the 4 plus 1 in the denominator, so I guess I could think of taking x to the 4 plus 1 and then plugging that into the reciprocal function. But if I take the derivative of x to the 4 plus 1, I get 4x cubed. And I don't just have an x cubed on the top, there's also this 4x. What can you do? Well, one thing you can do here is you can split this up. So what I'm going to do first, and so this is one that you don't expect to see right away. This is the sort of thing that you come up with once you've had several hours of practice with u-substitution. So I'm going to split it up. So the numerator, I can divide each term in the numerator separately by the denominator, and I can use properties of integrals to split this up and do it like this. Okay. Now, each of these integrals can be handled by u-substitution, and the two integrals, each one of them actually needs a different substitution. In the first one, I can do u equals x to the 4 plus 1. So du is 4, it's a bad 4, 4x cubed times dx. And I see the x cubed there, so let's multiply by 1 over 4 on both sides, and then that 4 is gone. So then x cubed dx is 1 over 4 du, and then I'm going to be left with simply 1 over u du. We can do that. What about this one? Now this one is a little bit trickier, and this is one where you really have to kind of remember some of your different integrals. And it turns out that the substitution you want to do here is, well, what you need to do is you need to recognize that x to the 4 plus 1, x to the 4 is x squared squared. If I let u equal x squared, du is 2x times dx. So 1/2 du gives me the x dx, and x to the 4 plus 1 becomes u squared plus 1. And what do we do with 1 over u squared plus 1? Well, that's the derivative of arctan u. So you can do u substitution in each of the two integrals, and each one you're going to get a different technique to finish things off, right? In the first one you're going to need a log function to evaluate, in the second one you need arctan. That's about as tricky as we can possibly get with some of these u substitutions, but you know, you could run into examples like that where you really have to think about it for a while. If you're seeing substitution for the first time, don't expect to be able to come up with that right away. It's something that's going to take a little bit of experience and a little bit of practice before you start spotting tricks like that. Okay, let's move on now, and we're going to see how to use substitution to evaluate integrals of all the trig functions.